my name is Gabrielle Graham, and I'm a current master's student at the University of Alberta. Today I'm going to share with you our recent work to identify and study the embedded stages of star formation in 11 nearby galaxies. In this work, we produce a catalog of embedded sources via visual selection. We then use this catalog of sources to train and test machine learning models with the larger goal of being able to use these models for identification in other galaxies. So to start, here we see an image of NGC 1566 as seen by JWST in the lower left and HST in the upper right. Stellar clusters are born in dense molecular clouds surrounded by gas and dust. As the cluster evolves, though, feedback from the massive stars will push the natal cloud of gas and dust away, leaving the exposed clusters that we see in the UV optical data with HST. On the other side of that, those dark, dusty lanes in the HST data are where we see the JWST data become extremely bright. It is at these locations where we expect to detect the early, still embedded star-forming regions. So how do we know where the stars are in all of this dust? With the power of JWST, we are able to resolve the 3.3 micron polycyclic aromatic hydrocarbon emission, or PAH for short, on the scale of stellar clusters at the distances of these galaxies. This infrared dust feature arises from small dust grains absorbing UV radiation, such as from young stars, and then re-radiating that energy in the infrared. Using the FINGS JWST Cycle 1 sample of galaxies, Rodriguez et al. 2025 show how this dust feature can be used as a tracer of the early lives of stellar clusters. However, in our work, we target galaxies in the Cycle 2 sample due to the availability of the F187 narrow data. This band measures the Passion alpha emission, which provides a strong secondary tracer for these earliest stages. Specifically, using the JWST Passion alpha alongside the HST H alpha data, we are able to use the hydrogen line ratio to trace regions of extremely high visual extinction. Essentially, what we're looking for are compact objects that are very infrared bright, but non-detectable in the UV optical range, or our HST data. So using these two tracers alongside two other selection criteria, our internal team used the Zooniverse platform to identify candidate embedded clusters across our sample of 11 galaxies. Here I show an example of what was considered an ideal candidate in our study, marked by the cyan circle in each image. You'll notice the source has a compact 3.3 PAH emission and a high Passion alpha H alpha ratio. We also require that the source have a point-like detection in the JWST F300 medium band, which is indicative of the underlying stars and hot dust. Our fourth criterion was that there be no discernible emission in any of the HST broadband data, and for simplicity of viewing in Zooniverse, we stacked these data into a singular white light image, which is the image on the lower right. So after classifying on all of our cutouts, we acquired a total of 10,749 taggings. These taggings are then grouped within a 0.3 arcsecond threshold, and any source with 3 unique taggings is taken as a candidate. This leaves us with an initial sample of 362 candidates, which we then reduce to a final catalog of 292 embedded cluster candidates after we do some final catalog cleaning. So here I show our final catalog across the 11 galaxies in our sample. Spatially, our sources trace the dusty spiral arms as well as the central rings when they're present. It is in these central regions that star formation is thought to be enhanced due to the dynamics and density of the gas. Using the photometric data, we also determine cluster properties such as age, mass, and visual extinction. Overall, we find that our population statistics are consistent with other catalogs of embedded clusters in nearby galaxies. We also find that the number of clusters in each galaxy scales with global star formation indicators such as star formation rate and the specific star formation rate, which the latter can kind of be thought of as comparing the active star formation versus the historical star formation. As mentioned, our second goal was to use this catalog to train and test machine learning models. Specifically, we make use of convolutional neural networks, or CNNs for short. CNNs are a deep learning algorithm that use a series of convolution and sampling layers to detect features such as curves and intensity in the input data. The extracted features are then flattened into a 1D vector which is passed through the neural network for classification. The network contains layers of connected nodes which use learned weights to transform the data from features into a classification probability distribution. Inherently, it acts like a series of filters that transform the data into predictions, and the prediction with the largest probability becomes the final classification. For training and testing of models, we adopt a binary labeling system. Label 1 objects correspond to our embedded cluster objects, and label 0 are other PAH bright objects. The secondary class of objects is drawn from sampling the 3.3 PAH maps for other point sources above a certain threshold. So that the selection of our classes is somewhat systematic, we also only include embedded cluster candidates from our catalog that were also found in this selection process. In the image of NGC 3059 on the right, the cyan circles mark embedded clusters which make it into the objects used for machine learning, or our label 1 class. The magenta circles then mark the other non-cluster objects for this specific galaxy. The objects in each class are then split such that we use 80% for training our models and reserve the remaining 20% for testing. One of our large goals was to assess the impact of data inclusion on model performance. As such, we produced separate models for 4 different data configurations. All the available HST data, including H-alpha, are used in all of our models, and we only vary the JWST data included. These configurations are chosen such that they reflect the data available in the FANG Cycle 2 galaxies, as well as the FANG Cycle 1 galaxies. As we produce models using 2 different convolutional neural networks, we end up with 8 model configurations in total. We then produce 10 models for each configuration, and at the end of it all, an object's classification label for a given configuration becomes the mode label across the 10 models for that configuration. Here I wanted to highlight one of the key outcomes that really gave us an idea of the viability of our final models. Here I am showing the distribution of the training label 1 objects, the orange contours, in comparison to the results of the test objects, which have a consistent label across all 4 models for the Cycle 2 configurations. In the case of a true positive or a false positive, this is a consistent label of 1, and for false negatives, it's a consistent label of 0. What we find is that our model is making relatively strong cutoffs in this specific feature space, meaning is heavily reliant on these features in deciding an object's final label. Broadly, this means that our models are biased towards labeling an object 1 solely if it has either a high 3.3 to 3.0 micron ratio or high Paschen alpha emission. On one hand, this could really represent the model selecting objects that we missed in our initial catalog, but most likely, we kind of infer this as needing to better balance our training sample as well as other hyperparameters in the models. So I will leave you here with our key results. If you want to continue to learn more about what we did, the full publication is available online, and thank you so much for listening.